My name's Jonathan Martin. I'm a scientist with CSU in Fort Collins, but I'm actually based in Denver at an urban and community forestry hub. And I'll talk a little bit more about that later. Yeah, sure. Okay. Today I'm here to present on physiological measures to identify new trees for our region. So we articulate to our communities the value of their trees, and we describe those as ecosystem services. This is a familiar term to us. There's a largely positive community view toward trees, but ecosystem services affords us a means to formalize and quantify and characterize the communities and their leaders, the value that trees bring to their lives. And it's quantified through a lot of study in a lot of different ways. And you probably share a lot of these examples with your friends and your neighbors, such as reducing ground level air temperature and urban heat island. That's a big topic in Denver where Spur is located. We talk about that all the time. Absorbing air pollution and dust is highly relevant to where we are in Spur, for example, because we're located in one of the most polluted zip codes of the United States. Other topics like lessening stormwater runoff, supporting mental and social well-being is an increasingly important topic that a lot of people are asking about in trees. And it's an opportunity for professionals to talk about the usefulness of trees. Wind and noise reduction, habitat, and increasing property value. A recent talk by Davey Resource Group made a really interesting comment about ecosystem services. Because you'll look at this list and you'll say, that's important to me, that's important to me. Where do they stand in terms of dollars? How do they quantitatively compare? And Data Resource Group, when they're going in on their planning projects, when they engage a community, often learn that although one category may not be the most important in terms of dollars, it's most important in terms of community values. And they'll prioritize their planning according to those priorities. I wanted to touch on one of these, and I know this graph looks amazing, but I wanted to walk you through it a little bit, and I think you'll appreciate it. It really struck me when it was presented by, thank you. I'm being told to move to the right. It struck me when Peter Ibsen presented it at Spur, at the meeting at Trees in the West. And so what it points to is the impact that trees have on ground level air temperature. This is the air temperature, not at the surface that you can see with the satellite, but the surface that you feel as a human. He said that as it gets hotter and drier, trees have an increasing impact on reducing the temperature that you feel. So they actually become more empowered to reduce temperature as it gets hotter and drier. And that's depicted in this plot here. So vapor pressure deficit may be a term you're unfamiliar with, but that's a measure of it getting hotter and drier. And then air temperature modification speaks to how is your experienced air temperature changing? Now, when you're looking at here at a building, it's going to get hotter day or night. If you're looking at an impervious surface, a little bit in the day, quite a bit more at night, interestingly. If you're looking at turf, which SB5 is addressing and is a hot issue in Colorado among professionals, it reduces it from zero. It's a negative impact on temperature, go turf. But it's stable as it gets hotter and drier. It is empowered. It doesn't increase its impact on the felt air temperature. Trees do, night and day. And these comments from his paper, I think, are really important. They're additive properties of shading and evapotranspiration. It's prominent in tree canopy, but not turf. Turf evapotranspiration is less likely to cool at human height. So a lot of the studies on temperature impacts are satellite based, but Peter and his colleagues are really getting at the human experience, which is more translatable. So The size double the benefit. So shading and increasing total transpiration as trees become taller and more mature. This is key to this talk, taller and more mature. I'm going to plug Trees in the West. This is a meeting at which Peter presented these data, among other scientists who spoke to us about air pollution and air quality. It's an annual meeting. The first meeting was about social equity. The second meeting this year was about climate adaptation. And we're working on the upcoming theme. So if you have an interest in these topics, please attend in person or online. Okay, hopefully your cell phones are not inactive. If you shoot that barcode, you can contribute to answering this question in an interactive way during this talk. I should have told you to keep your cell phones, smartphones on hand. So what I'm wondering about, and this is a question that comes to my mind often, is in your area of responsibility, what would you estimate is the average lifespan of an urban tree? I hear a lot of different comments on this question. And I think taking a popular survey, at least in this meeting, could be interesting. And maybe it would be interesting to you too, to see it live. It's on the low end, isn't it? Some people are betting up. I've heard at ProGreen in 2025, I heard the number drop 8 or 9 years by a pretty experienced urban forester and arborist. Okay. Not bad, 42. Nice sample size. Thank you. So it's pretty heavy in that. Well, it's not, okay, less than 10 years is here. I didn't expect it to rank it in terms of prominence, but that's a cool effect. So 10 to 20 years. It's on the low end, but not on the extreme. It's definitely not here or here where we want it to be, where we aim for it to be. And those who are studying this question will point to a broad study across a larger geographic area of about 20 to 30 years. And they'll point to stressors and mismanagement shortening lifespan. The survey here may speak to our community more in a more specific way, and hopefully that came across. And those who are studying the topic also are reporting on findings that are probably pretty acceptable or pretty understandable. The increased age and size yield substantially more services, and that really young trees that maybe are dying due to stressors or mismanagement really yield limited services. So we really need to get the trees larger. And hopefully this is just background, and I'm just preaching to the choir, right? And then planning and long-term investment are really what we need to emphasize to get toward these large mature trees to yield these ecosystem services for our communities. And Carrie told me once when we were in the office, she said, you have to place good bets on which species you choose to plant. And we know that abiotic and biotic stressors bring about sudden and substantial mature tree species and genus loss. That these abiotic stressors can lead to biotic stresses and pest and disease. And one of the pests that's really on the tip of our tongue right now is emerald ash borer. Mel gave a great talk. And we look at the prominence of ash in our cities in Colorado, and we're hearing city managers and foresters talk about management to mitigate the absolute loss of these trees and their prominence by count in our cities. But the expectation is they're going to take a big hit. And that we have to make good choices about which tree species we choose, or genotypes, or genuses, to replace those that we expect to lose. And diversification is a strategy that can reduce the impact of this loss is going to have on forest scale canopy loss. But what diversification requires are options, choices, and not just as an eventuality, but maybe on a more immediate term timeframe. The abiotic disasters might even cause even more acute problems. They overwhelm arborists and public resources, and they require forest scale canopy restoration. It's one thing to lose 10 to 20% based on an attack on ash. It's another thing to get wiped out. So we need to be cognizant of this threat, but we also need to take into account where our climate is going. And it's a tricky calculation, isn't it? And it's also a hotly debated issue. We're placing some trust in experts and scientists to study the numbers, and we're highly fortunate in Colorado because we have fantastic climate scientists at CSU and at the state level. And they are generating Colorado-specific climate reports that we can refer to and gain perspective on where its climate is going. Please.
What's this resource here? I think you are.
Yeah, please shoot the QR code if you're interested in accessing this resource. I'm sort of building toward it, but I should go straight ahead at it. So this is an interesting tool. So climate analogs are described as identifying regions that represent where you are going over a period of time. So this is a 2080 estimate based on a high emissions scenario, and that refers to greenhouse gas emissions.
Is that the 815?
I don't know the model for reference, if that's what your question is getting at. Is that what you're asking?
Yeah.
So John, the QR code's not functioning,
Oh,
so that's part of the implication.
4.5
mhm.
for us.
Uh-huh.
And then there's other people that use 8.5.
I don't know the answer to that question, but I'll find out. I'll find out. Sorry about that. I think I've heard the emission scenarios be described according to the models that you're describing. I can say as at the very least, it's the high emission scenario, but I can't pull the number off the top of my head. I should, because I just went to the Climate Hub launch a couple of days ago at Spur, and they were referring to these very models, but I'm not an expert in climate science myself. So I wanted to put up the Grand Junction example here, perhaps relevant to this audience. I'm sorry, but I tested it and it doesn't work. Okay.
I'm trying to find the resource that you used.
Okay.
So I'll
Okay.
give an update. If I find
Okay.
it.
Okay. So you can use this resource to basically punch in a zip code and get an estimate under a high emission scenario, what your city is going to be comparable to by 2080. And Washington, Utah, down near St. George, is the analog to Grand Junction for a 2080 estimate. So this is where it's going. But it's worth pointing out that that this is an estimate. It could vary along this path depending upon human behavior. And we all have maybe different perspectives about how things might turn out. But I think it is a useful tool, and it's an eye-opening tool because I've been to St. George several times in the summer, and I remember my shoe soles getting pretty soft on the tarmac. So speaking to this climate change in Colorado, this 2024 published report, the general conclusion or assertion is that it's going to get hotter, it's going to get drier, but that it will continue to involve cold. We're still going to have low temperatures. And maybe that's a theme in our region in general. We're used to hot and dry, but we contend with cold.
That's the website. I'll put it in the chat for the
Thank you.
people.
Thank you. Thank you. So I think an important tempering observation when you look at these assertions is the confidence. It's a good thing to be mindful of. They have very high confidence in some of these, but in others, medium. But some of their quotes in the report that by 2050, the average year is likely to be as warm as the very warmest years on record through 2022. And there have been significant increases in extreme heat across most of the state. But the decrease in extreme cold has been more modest. So we can expect to still have to put up with cold. So if you're thinking about what tree species make sense for the future, you might think hotter and drier. Okay, but they need to be multimodal in terms of their performance. And that's where our focus is on heat and drought stress tolerance, but also on cold hardiness. So new, well-justified options are needed to diversify urban forests and to proliferate and sustain canopy in the faces of these threats and stressors. And we need to be looking for adaptation, climate resilience, rational provenance, that's the source, the geographic region that you're pulling these species from. For example, southerly, mountainous, seasonally cold regions. But a very important topic is coherence with stakeholders, such as city regulators, nurseries, landscape architects, contractors, and consumers. You can force a tree species you think is fantastic down the throat of the community, but if they're not bought in from their own logic and their own professional standards, you're going to fall flat. And I talked to JC and Chris, who are landscape architects, about this question. I said, hey, if I could pitch you really good justification, scientifically speaking, for a new species, would you go with it? And JC said, my arms are already outstretched. I want to work with new design potential, but I can't because I'm constrained to what cities will approve from me. You have to get through to the regulators and foresters. You have to convince them too. It's a nested and dependent. You fail at one, you fail at all. And Chris said, I use what species are available on the market, what I can get. Okay, you need to convince a nursery to invest, to do it. And Dan, before I move on, Daniel Burcham would say that when you're talking about identifying species, it's difficult with limited information to judge the compatibility of trees, potential trees, with changing conditions. And so we're turning our attention to rapid and quantitative physiological measures. We view that they're needed to complement, but not replace, observational approaches to tree selection. A lot of tree recommendations rest on expertise, experience, observation, and trialing. But that's expensive in terms of time. And we were just talking about, or I was just talking about, that time may be something we don't have a whole lot of if we're facing abiotic stresses and biotic threats that are coming in hard and fast. We need to be faster. And we need to be right. And so some speakers at the Green Expo in Denver in 2025, Barkley and Dickey, they gave a great talk about the effort and time that's involved to develop a cultivar for market. And it was a large number. It was 15 plus years. And some of them don't make it. They don't make muster, or they don't pass muster halfway through. So you get maybe 10 years into the process, and some of your candidates up to that point were doing well because they have a very high standard in terms of the cultivars that they release to market with good reason. And the choice of these tree species can often be observational, qualitative, subjective, and anecdotally based. It's a well-reasoned source of justification for species adoption, but we feel that it's important to complement it with physiological measures. And I pulled out a couple of images here that speak to the question of cold hardiness. And both images actually point to the same observation about cold hardiness, is that if you take an observational approach to identifying the candidacy of a species for a region, an observational approach to cold hardiness, You could be tricked because this pear bark sloughing off came a year after a severe fall freeze. And this, the needle browning was delayed until the temperatures warmed in spring. So if you're trying to decide whether or not a tree is performing sufficiently from a cold hardiness standpoint, by observation, you won't know what cold event during your winter led to that outcome. Was it the cold that we had in December? Or was it the cold we had in January or early March? Or was it all of them? Just how cold hardy is this tree and how does it compare to another tree that we're interested in? You need to be able to make those comparisons. And we know that cold hardiness is important. I mean, certainly because of the things I've just said, but it's a widely established trait for determining the geographic distribution of trees. And so this is mocking up just a simple sort of workflow of species proposition, physiological testing, either deciding to propagate or postpone being an interesting word. If climate's moving in the direction that our experts are telling us, we'll probably get around to revisiting those trees before too long. But who's ready now is a question. And then planting and stewardship. Here's your second interactive question. Will you shoot and report? That was about 50% on the last one. So what extent of freeze damage do you tolerate among trees in your area, particularly for the first years of planting? I've asked this question of some colleagues and I got really interesting answers. And I'll give you one example without mentioning her name. She said, when I walk into a nursery and I'm looking at stock, I won't tolerate any. But when I'm out in the field and I'm responsible for a tree in my city, I'll put up with it. I'll give the tree a chance. I think that's an interesting comment about different stakeholders and their standards for managing and accepting cold hardiness. Look at the nurseries and what risks they face into those contexts. I can't afford for it to be shut die back and sell it to somebody who's going to buy a bunch of trees for my city. And look at the forester who said, I'll give it a chance, I'll work with it. I need that tree. I'm not going to just pull that tree. I'm not going to put a crew on that. I want that tree and give it a chance. Okay, here's pretty low tolerance, but okay, 10 to 25 is catching up. Hopefully these results are interesting. They're interesting to me. Okay, thank you. So we embarked on standing up a method at CSU, a method that actually has it's pretty well established in the field. It's being used by some interesting groups. Daniel Burcham leads the group. He's a professor of arboriculture at CSU in Fort Collins. And if you haven't met him, get to know him. He's fantastic. And these are also fantastic undergraduate research assistants that were looking for lab experience and join the effort. Electrolyte leakage is a somewhat laborious method, as robust as it is. So Max, Cole, and Nathan joined, and it was very helpful. This is what I look like in the laboratory executing the method, particularly before the undergraduates joined the effort. This is a programmable freezer. So what we do is we go out in the field during the winter and we will trim off young twig tissue, 1 to 2 year old, pretty narrow diameter. And we'll cut that into little segments and we'll put each segment into a tube. And then we'll put those tubes, the segments are immersed in water. And we'll put those tubes into racks and we'll put them in the freezer. And then we'll instruct the freezer to start pulling the temperature down. And then we will pull those samples, some of them, out at each temperature. So every single tree taxon that gets submitted to this experiment is going to be producing segments. Let's say we harvested at the beginning of January. They're going to be producing segments that see 4 degrees C, it's lightweight, that's about refrigerator temperature, or negative 10, 20, 30, 40, or negative 70 degrees. And at some point, the tissue is going to suffer freeze damage in that freezer. And we can pull those segments that are immersed in water over to the bench and we can measure the conductivity. If the tissue starts suffering damage, the cells will break, their contents are conductive, All the ions inside the cells are conductive, and we'll measure it. And we'll see just how much damage is taking place as they get exposed to more and more damage. They're not going to stand up to -70 for the most part. Well, a cottonwood will, but some won't. Where will they start to burst on this? And at what time of year? At the beginning of January, they're probably going to be more tolerant. At the beginning of November, less so. This is what the data looks like. And I hope this isn't too painful, but I wanted to describe some of this in hopefully simple terms, so you could appreciate what we're looking at. And so what we're calculating is percent injury between a range. So down here at 0% injury, so percent injury is plotted on the y-axis and temperature is on the x. So down here at the right, where there's 0% injury, this is like 4 degrees, no problem. And I didn't mention it before, but after we run those samples all through those decreasing temperatures and measure the conductivity of the samples, we put them in a bath of liquid nitrogen, which is down at 196 below 0 centigrade. And we just rip those cells to bits. And then we measure conductivity. And the intent there is to inflict maximum death on those cells, maximum injury. So we can use that as a reference in our plot. That's 100% right there. Okay. Now, at -70, some of those points there are actually starting to be equivalent to that liquid nitrogen inflicted death. They were already blown up. Liquid nitrogen just basically didn't have anything to do with samples or didn't have an additive effect there. But as you plot these data points and you're calculating, you're expressing that in terms of percent injury, they fall along a curved line. And each of these curves here, like for these genotypes, so this is a cultivar Royal White of Cercis canadensis on Ames, Iowa, Provenance of Cercis, or Appalachian Red. You can look at these plots and you can estimate what's referred to as the lethal temperature 50. The lethal temperature 50 is the temperature at which 50% of the tissue has been damaged by freezing. And these are actually the estimated numbers here for samples that were collected in mid-February of 2025 for Cercis for these genotypes, as an example. So this is what we're actively engaged in doing. For 14 taxa over the cold season of 2024 to 2025, starting in early November and ending in early May. So we went wide range in terms of date, and we were testing tissue samples every other week to capture that season-long temperature progression and to survey where along that progression those species are measuring in terms of their hardiness. Some of them are familiar. So this is looking at a figure that people are probably interested or familiar with looking up. Minimum cold hardy estimates. Say, well, how cold hardy is Eastern redbud? And you'd look it up in a publication or in a textbook, and you'd say, okay, it's been seen to be down at around -35. And these are the cold hardiness zones for Fort Collins, where we were pulling these samples as a reference. And these are seasonal minimum temperatures for the last 5 or so years from the Fort Collins area where we were pulling these tissue samples. Okay, this is out of a textbook. What did we see? That's a little pale. Sorry about that. It's right about there.
Sorry, your slides are offline for online. They're not seeing this, and I don't know.
Oh, weird.
They're seeing the previous slide.
That's strange.
I know.
It's
Are you still seeing the previous slide, Allison?
It just switched.
Is it-
So
delayed.
there's a slight delay.
But like minutes, because I didn't,
minutes.
yeah.
Oh, bummer.
Okay, so we'll let you know. Thank you.
All right, okay. I don't quite know what to do about that. Okay, I'll just try to press on.
Yeah, keep going.
Okay.
I just wanted to make sure that you were talking about super great stuff, that it showed up on the other side.
Okay. So from our own measurements, you'll see that we measured some examples. I'm using it too much, I guess. We measured examples that were above or below published references for the species.
You want, we can use the.
Oh, that's cool. Thank you. And if you're relying on these numbers, it might encourage you to go in a given direction. Such as here for Arizona cypress. You might say, oh, well, that's great. They're performing better than reference. And it looks like Carolina sapphire might be a really good choice. Okay. This line here, orange line, is the 2025 absolute coldest temperature for the year. And these are the minimum temperatures that we measured for each. Okay. It's useful information. I wanted to point out, though, that the Gamble Oak was not published and couldn't find anything. So this might be highly useful new information. So you might say, okay, you can make some choices based on these data. But what those data fail to appreciate is that cold hardiness is a dynamic trait. Attaining absolute maximum maximally cold hardiness is important. But what matters most is that if you're a tree, you're cold hardy at the right time, when the right temperatures, or when it's cold, and you don't really need to be cold hardy when they aren't. Unfortunately, it's not coming through on this plot. But this black band represents ambient temperature. I'll just describe this plot to you so you understand what we're looking at. This describes ambient temperature throughout the season. And these data points are plotted LT50 values derived using the bench methods that I was describing a little earlier. And this is for Cercis, the 3 genotypes that we tested. And I wanted to take this plot to show you what the data looks like, what we're looking at and analyzing and thinking about, and to point a few features out. There's this acclimation period earlier in the season. We reach maximum cold hardiness, and there's a deacclimation for the spring, in the spring. And we're looking at different factors. We're looking at the timing, the rate of acclimation and deacclimation. We're looking at the degree of hardiness, and we're looking at maintenance or stability of hardiness. These are all sort of like performance metrics where you could say it's important if trees acclimate rapidly before they might get caught off balance by cold, or that they deacclimate slowly and don't get hit by a late season frost, or that they attain sufficient cold hardiness, or that they maintain cold hardiness. Here you would point to a degree of instability. When I showed this data to Carrie, she said, dead bud, right? That's what she said. We might be seeing an example in a data set of why that is. It's maybe an instability. Do we understand the signaling? Do we understand mechanism? That's a deeper, more technically sophisticated question scientifically, but we might be able to see it. And if we see a candidate species, or we're testing a candidate species for our region, and we see instability, we might get concerned about its candidacy, especially if that instability occurs at a specific time. This is zooming in on that maximally cold time period. In the same data set, you see that Cercis is on the left, and you'll see those data points look pretty familiar. And what I'm bringing into this slide are these asterisks. They point to statistical significance between the data points. They're a little tricky because I didn't want to get too busy in the plots. But basically what this blue asterisk means is that the blue data point is statistically significantly different than the green data point. Again here, because the asterisks asterisk is colored blue. It's marking the green data point that points to this pairwise relationship between these two. These asterisks are marking the green data point, but they're both blue and red. This Van Buren County is significantly different than both the Royal White and Appalachian Red in terms of its LT50 at that date. So you can start to look at the statistical significance and the difference. So it's not a cursory look at these plots that are leading us to interpret the data and make some conclusions about this. We're running stats, and the stats are pointing to significant differences between these LT50s, and that adds a lot more power to the data. You can start to stand on it, and you can say, this is something that can be more, stands up to greater technical scrutiny. And you can start to draw more, base your recommendations on these comparisons a little more so. So you might look at this comparison here and say, all right, Van Buren's looking pretty good. You can't see it in this plot, and it's very unfortunate that you can't. So I'll describe it really quickly, but these black lines are the mean low temperatures at those dates, which you can't see in the plot, but which I can see here. Huh?
Love Street.
Oh, yeah.
Oh, you can see it over there. That's weird. All right, so look at the left street. What I wanted to point out is that at this low temperature here, this is actual. That's the low temperature that occurred at that date. And it spikes down. And, you know, when it kind of stabs into the Appalachian red. So what that is showing there is that the LT50 is overlapping with ambient temperature. And basically, it's doing damage according to our calculations. But then Buren is getting more scot-free. Now you might say, well, Royal White's in the hunt, but if you take it to a level of statistics, which is a higher level of scrutiny, it's hard to say that. It's a little bit unwinnable in this case. But this is just a nice example of pointing to an instance in the data set where the results would raise your concern with the candidacy of Appalachian Red for its use. Now, does it blow it out of the water altogether? Maybe there's some things you can do. I really want Appalachian Red. I'm going to be careful about where I put it. For example.
John, you have to come closer to the mic once you're done pointing this out.
Okay. I want to be able to, well, I'll be able to see.
Welcome to the next one.
That's cool. So these are the kinds of incidences in the data set that pique our interest and might steer your attention to one cultivar or one genotype versus another for our region. Now, I put this in here as something that you might be tempted to do. Like, dang it, well, for Hesperocypress, we missed. If we had been testing every week, we might have been able to really catch those data points right there, where the low temperature is. So maybe we could draw a line and we could kind of estimate, from a scientific perspective, that's usually not encouraged. It is better if we had just got those data points. So is it a look at the two, the Carolina Sapphires, maybe? So Carolina Sapphire is showing maybe a little more susceptibility is what I would say here, and Cook's Peak is looking a little bit better. I would probably look toward Fandango. There, Fandango is staying low. It's showing some good stability. And that's an encouraging, let's say, expression of cold hardiness data in this test. And I wanted to include the Quercus data. Quercus affords an opportunity to talk a little bit about inclusiveness and diversity. So one of the pitfalls to looking at these data is that you would be inclined to choose the winner.
who's the best? You know? And I think that maybe even in the public view, that's a common perception. Well, what's the best tree? What's the lowest absolute risk? I'm only gonna plant one tree on my property, single family home. I just need the best. And that's dangerous because we're not trying to pick the single best tree. We're trying to be as inclusive as possible and diversify our forests. So we need to be as inclusive. What's good enough? What's making the cut? So if you look at the plot over there, you might say, all right, in late January, Gila monster is looking a little more susceptible than its partners. But Gila monster is nowhere near the low temperature on the day. I mean, look at that low spike. Gila monster is fine. Okay. Good enough. What's your risk tolerance like? How much do you value diversity? How are you going to look at these data sets and act on it? So you have to be careful, or you'll have to define your intent. I want to turn a little bit of attention to this set of data. This is the acclimation. Just a couple of comments on this. They're really queuing up together in the time of season. So that's replotted here on the upper right, and you can fit a regression line to that, and you can estimate the acclimation in terms of loss of degrees. Loss of degrees per day. And you can start to compare genotypes. You might express that losing cold hardiness at a slow rate is advisable in terms of performance. They can hold on to it late, and they might be more resilient to late season cold. And that stands up to logic. And we're thinking about this. This is sort of our first data set. So the cold hardiness at bud break out there at the end of our series there, kind of late April, early May, were pretty comparable across the genotype tested. They all kind of came out to a similar level of cold hardiness. What appeared to be more different with the data set is where they start. If you go over there to the left end of that plot in late March, some of them are in late March are quite a bit more hardy than others. And so the steepness of that line appeared to be more related to that starting point of cold hardiness. If they start really cold hardy, the line's going to be sort of steep to the finish. So we need to think a little more deeply about the acclimation. This is an early look. Okay. So that's what we have right now with regard to hardiness. And that's where most of the presentation rests. But I wanted to mention some of the other efforts that we're involved in with regard to water use physiology at CSU Spur. So at Spur, we have an urban community forestry hub. Oops, sorry, Katie. And it's comprised of different groups coming together to work on the subject. So here are some members of the Colorado State Forest Service who are members of the hub. The hub is led by Carrie Tomlinson, who's pictured in the center, and who's here today. If you don't know Carrie, introduce yourself, Carrie.
Say good things about it.
Say good-
Boss.
I'm one of the scientists who's a member of the hub. I'm located at Spur, but Daniel and Troy are up in CSU in Fort Collins. And then there are partner organizations. Allison is speaking today from Colorado Tree Coalition. Chris Hawkins from the Nature Conservancy, and certainly Dana Coelho from the U.S. Forest Service are huge contributors. So I'm going to have to move through it kind of quickly. But what I wanted to say is that species use highly variable amounts of water. This is expressed in terms of water use per tree. on that column. And if you're up high on the coastal redwood, it's actually relatively low in comparison to the London plane tree. It's over an order of magnitude of difference in terms of water use per tree per day. And this is an important topic to look at because we can either support or caution against specific tree use, and we can identify genotypes for cultivar development. We can bring comments on tree affordability from a water use standpoint. I encounter this question frequently. We can't afford to grow trees, they use too much water. Look at the size of that tree. I think that perspective would ring true with the coastal redwood expectation here in this plot. It's doing weird things. Okay. We can inform urban water use or water use through forest managers and also cities for water budgeting. And we can identify water movement in tissue that lead to the onset of stress. And we can inform and increase the impact of tree care professionals in the region. So we created a research building spur, and we planted 10 replicates each of 8 different species, and they break into roughly equal sized groups or numbers of species for high water use and low water use. And the plan is to measure water use under prevailing irrigation and weather at this grove, and then also measure tree tolerance to a recovery from simulated drought. The drip system used to irrigate the trees has valves at each tree, so we can actually choose which trees undergo stress in a contrived way. The trees post-transplanting are looking good. These are some images of coffee tree and small linden from this spring. And they're arranged randomly in the plot, and they're spaced 10 feet apart from one another, which is tight. But we're getting the sample size up for our studies. We're really just looking within a few short years after transplanting at young trees and their water use in this context. The instrumentation being prepared for the studies are called dendrometers, and they're being prepared by Troy Tree, and iron brazing oil has been very helpful to fabricate these dendrometers. And you can see the image in the middle there of the white, sort of blocky looking instrument. It's basically similar to putting your fingertips down onto the stem or trunk of the tree and being able to sense minute changes in tree diameter when water is flowing through that tissue. So you can quantify water movement through tissue by virtue of the small changes, expansions and contractions of the tissue in time. And so if you ascribe out those dendrometers at scale to 80 trees, with 10 examples of each of the 8 species, what we're looking for is a statistically powered quantitative measure of water use in those species. Okay. The news is that the sensors are not yet out, but they are on course for the first 30 to be deployed to the trees, and then the other 50 would follow. Something that's going on in parallel that's a little more nascent in the grove is actually soil moisture sensing. There's a group led by a faculty member at CSU in JM, and he develops sensors, micrometeorological and soil studies sensors, and their soil moisture sensors have been installed at the grove. And Jay and his colleague Ian haven't yet used their sensing technology in an arboricultural context at all. They're mostly working in agriculture. So this affords an opportunity to gain the sensing technology at the grove in the context of water use studies in tissue with the dendrometers, to demonstrate some data and use of this sensing technology to professionals in the field of arboriculture. And yes, to inform irrigation management for ourselves and perhaps speak to the use of sensors for that purpose. Now, the positioning is with the sensor plunged right down at the surface,
next to the trunk. You can say the first few inches, depth of soil. And then also, if you look at that right photo, you can see those little orange capped sensors. Those are like, they're almost like little fingers that we just horizontally press into the soil about the root ball. And they're down at about 8 inches deep and about 18 inches deep. And actually have them on the side of the tree and actually just down slope of the root ball because the trees are planted on a slope surface. And this is just a look at what the data traces look like. This is pretty new information. So I just wanted to share what we're starting to look at and thinking about integrating into tissue studies. But those, you can see here, the blue line is actually that surface level sensor or probe. And it's picking up irrigation spikes. That's when I program the system to irrigate. And you can see the dark purple and dark green lines are the deep sensors. The green is at sort of 9 o'clock position and the purple's at 6 o'clock position. And the lighter colors are the shallow sensors. So you can start to see on a depth basis how much moisture is getting in. It's expressed in terms of volumetric water content. That's the amount of water per soil measure. But we can start to look at the water's getting in, how deep it's getting in, to what extent, and how long it's holding as it sort of declines in terms of content, and where you stand with respect to field capacity. Okay. That's it. So I put up a couple of questions that interest me, but I'd be glad to answer the questions. I know I'm probably out of time. And
We have
it's
like
almost
1 minute,
1 minute.
so.
All right. Cool. I am always interested in this question because there are so many passionate people in this community about species choice and selection and work very conscientiously with the species that are prominent in the field. But a lot of people are looking to the head independently on their own, and oftentimes they are performing at their own scholarly level in terms of where they think things are going and what species are interesting for the future. And so even if you don't like raise your hand right now and shout out the name, I'd be interested if you feel really strongly about the potential candidacy for a species in the future to learn about that. And not only to learn about it in general for Colorado, but in this region. These methodologies can be translated and utilized on a pan-region sort of manner. You know, it doesn't all just need to be in 4 columns close to the lab. You could be pulling tissue samples from other places. And so getting a species out here, maybe you like one of those and you want to see it perform up here, retest. That's just a comment I have. I think I already spoke to the second one. And I think it's time to eat. All right. Thank you.